Good morning, sir. My name is Bhargavi. I am from second year in EC department, and my roll number is 234G1A0421. And I got a topic for numerical problems in Bodo Plat in control systems. And my topic is numerical problems on Bodo Plat. And let me explain, sir, what is a Bodo Plat. A Bodo Plat is a graphical representation of a system's frequency response, typically consists of two plats, and one showing the magnitude or it called as gain, and other showing the phase shift, both plotted against a frequency. Both plots show the frequency response, that is change in magnitude and phase function of frequency. And here I take an example, so and for example question is, for the following transfer function draw a Bodo plat and obtain a gain crossover frequency, where g of s is equals to 20 by s into 1 plus 3s and into 1 plus 4s. The solution is the sinusoidal transfer function of g of j omega is obtained by replacing s by j omega in the given transfer function. When we substitute s is equals to j omega, we get 20 by j omega into 1 plus j3 omega and 1 plus j4 omega. And here when we find the magnitude plot, the corner frequencies are omega c1 is equals to 1 by 4, uh, that is in decimal form 0.25 radians per second, and omega 2 is the second corner frequency is 1 by 3, in decimal form is 0.33 radians per second. The various terms of g of j omega are listed in table 1 in the with increasing order of their frequency. Also, the table shows the slope contributed by each term and change in slope at the corner frequency. The columns of the table taken as terms and corner frequency in radians per second and slope in decimals and change in slope. When we take first term 20 by j omega, there is no corner frequency, and here slope is minus 20 because the j omega in denominator, there is no change in the slope. And when we take a 1 by 1 plus 4 j omega, the first corner frequency is 1 by 4, that is 0.2 in z decimals, and the slope is minus 20 because j omega is in denominator, and the change in slope we get minus 40. And a third term 1 by 1 plus j omega is 1 plus j omega, the corner frequency is 1 by 3, that we get 0.33 in decimals. The slope is minus 20 because here also the j omega is in denominator. The change in slope we get as 0 because minus 40 minus 20 we get 0. We get minus 20 as a change in slope. Here choose a frequency omega 1 such that omega 1 must be less than the first corner frequency, and choose high frequency omega n such omega h such that omega h must be greater than omega c2. Let take omega 1 as 0.15 radians per second and omega h is equals to 1 radians per second. Let a is equals to magnitude of g of j omega in decimals. Let us calculate a at omega 1, omega c1 and omega c2 and omega h. At where omega is equals to omega 1, a is equals to magnitude of g of j omega is equals to 20, the formula is 20 log 20 by omega 1 0.15, that we get 42.5 decimals. At where omega is equals to omega c2, a is equals to g of j omega, 20 log 20 by 0.25 we get 28 decimals. And at where omega is equals to omega c2, here the formula changes into a is equals to slope from omega c1 to omega c2 into log of omega c2 by omega c1 plus at a at omega is omega c1, we get minus 20 into log of 0.33 by 0.25 plus 38, we get 33 decimals. And here also when where omega is equals to high frequency, the slope changes into slope from second corner frequency to higher frequency into log of high frequency by second corner frequency plus A at second corner frequency, that is equals to 60 into log of 1 by 0.33 plus 33, that we get 4 decimals. Here when we find a phase plot, the phase angle of g of j omega, that pi is equals to minus 90 degrees minus tan inverse of 3 omega minus tan inverse of 4 omega. The phase angle of g of j omega are calculated for various values of omega and listed in table 2. And here the columns of a table 2 is taken as omega in radians per second and tan inverse of 3 omega in degrees, tan inverse of 4 omega in degrees, and pi is equals to g of j omega in degrees. Points in plot, and the values we got for the omega value 0.15 is approximate minus 146 degrees, and for 0.2 is minus 160 degrees, and for 0.25 is minus 172 degrees, and 0.33 is approximate minus 188 degrees, and 0.6 is minus 218 degrees, and for 1 is minus 238 degrees approximate. And this is the graph for the values and magnitude plot and phase plot. Here the scale for magnitude plot, the y-axis taken as 1 unit is equals to 10 decimals, and for phase plot the y-axis unit taken as 1 unit is equals to 20 degrees. And advantages are simplified stability assessment and easy visualization of frequency response, and straightforward margin determination, design tool for control systems, and asymptotic approximation. And thank you, sir, for listening my presentation. Thank you.